All right, so this is now a truss method of sections example problem as a review for the final. Let's see, method of sections. We're going to do F1611. I think I had actually done F1612 before and shared it with you, I believe. Or maybe we did it in class. But so for 1611, they give us this truss. And it's been a little while since we did this, so you may want to review what we talked about in class about these or review the book. But basically we have this, we have this truss. Let's see, A, 1, 2, 3, 4. So 1, 2, 3, 4. And feel free to look in your book to see what the problem actually is. So, it's rollers over here. This is point E. Let's see, this is point D, point C, point B, and point A. Each of these are 2 meters. Maybe I'll draw those in a second. And then up here is point H. And then point G is up at the very top. Point F mirrors H. And I think that's it for the point. So let's connect everything together now. Nope. G to F. G to D, F to D, and F to E. I'm going to write down some of the dimensions that we have here. So 2 meters, basically all of these are 2 meters. The height here is 2 meters, and then from here up to here is 1 meter. And let's see, and then we know some forces. Let's see. From B we have 10 kilonewtons. From C we have 25 kilonewtons, and then from point D we have 15 kilonewtons. And let's see, this is phi. They have that on the drawing. So they want us to find the forces in members GF, GD, so GF, GD, and CD. So with this we can actually draw a section through this, and that'll help us get all of those. So I'm going to go ahead and write down, so they want us to find force in members GF, GD, and CD. And then they want us to state if they're in tension or compression, so tension or compression for each. So if you remember for these, when we solve these, often what we can do is the first thing is we can just look at the overall free body diagram to figure out what's happening at AX, or at the A side or at the E side. So I'm going to go ahead and draw a free body diagram just for the whole thing. Let's see. So we've got point A, we can have an AX and an AY. Then we have the whole truss system. And then at E, we're just going to have the EY because we have those rollers. And then we have those forces, so 10 kilonewtons, 25 kilonewtons, and 15 kilonewtons. And those are each 2 meters apart. So with this, we can just, we have basically 3 equations that we can use. So we can sum forces in the x direction, sum forces in the y direction, and do moments to figure out these. So we could start just with we could sum the moments about A, since there are 2 unknowns at A, and those are going to equal 0 in static equilibrium. So the sum of the moments about A will make out of the paper being positive. That equals that 10 kilonewtons, and this one would be negative. So negative times 2 meters minus 25 kilonewtons times 4 meters at perpendicular distance minus 15 kilonewtons times, so that's 2, 4, 6 meters, 6 meters, plus EY, the way we have it drawn here, 2, 4, 6, 8 times 8 meters, and that's going to equal 0. So we have 1 unknown, so that's awesome. So I'm going to pause it and do the calculation. So I just did the calculation on my calculator, and I got EY equals to 26.25 kilonewtons, and that means I did good in the direction, so it actually is going up. Alright, so now we have EY. Now we can sum the forces in the y direction, and that'll just give us that AY. So let's sum the forces in the y direction equal to 0. For that, we're going to have AY, so that's AY minus 10 kilonewtons minus 25 kilonewtons minus 15 kilonewtons plus that EY that we just found, 26.25. And that's going to equal 0. So we have 1 unknown, so we can find AY now. I'm going to pause it and do the calculation really quick. Alright, I got AY equal to 23.75 kilonewtons. And then we can sum the forces in the x direction equals 0, and that equals AX, because that's the only one. So AX is 0. So that gives us a start. So now we're going to do, now we know what's happening at the ends. I think this is a step that some of y'all would skip. So now that we know, and maybe we could have actually stopped there. So we're going to do, let me get another color. We're going to take this section here and take a look at it, just because it looks like we'll have less going on there. We know EY now, so we just found that EY. And hopefully with that, we'll be able to use some of the forces in the X, some of the forces in the Y, and be able to figure out what those unknowns are. So let's go, I might actually copy this. I'll just copy this here, this section. And then we're going to go ahead and draw our free body diagram. And I'm just going to go on to a new page so we have room. So here's our section. And now I'm going to draw a free body diagram. So basically we have this FDE. At E we have, oh wait, it's a different color. At E we have that EY, which was, what was it, 26.25 kilonewtons. See, this is E. Oh. And at D, we have 15 kilonewtons. We also have this force here, which is going from D to C. We have this force here, which is, let's see, D to G. And then we have this force here, which is F to G, I believe. Yeah. And let's see, this is F, E, and then we know a little bit about the dimensions. This one's 2 meters, that one's 2 meters. I think they had originally told us that this angle here was phi. So they had named it. And yeah, I think that's it. Oh, I guess, yeah, we know that's 2 meters. And then we also know that let's see, well, let's use a different color. So if we wanted to go and take it all the way up to point G, I guess there's not anything there. So I'm gonna erase that. But that point G is basically, how well y'all can see that. It's another 1 meter. And it's also 2 meters over from here. It's probably not the best color. But so we do know something about that geometry, I guess, is the point there. All right, so now we need to get into some geometry. Let's see, so we know if we extend this out to point G, that's another 2 meters. And then it was 2 meters up to here, and then 1 meter. So we basically have this triangle, so I'm going to redraw it from D up to G and over to C. So this is that angle phi. We know this is 2 meters. We know this side is 3 meters. And I guess that's about all we know. So that works though. So now we can find that phi. So tangent of phi is going to equal, what is it, opposite over adjacent. So tangent of phi equals 3 meters over 2 meters. So that'll give us a phi equal to 56.3 degrees. Well, let's just go ahead and carry it, 56.31 degrees. So that'll help us with figuring out that DG. And what else do we need? Let's see. We also need to figure out the angle of this FG. So let's draw that triangle. So let me pick another color, maybe pink. So with this, we have this triangle. So F, we can sort of, I guess we can sort of make a triangle. F over to here, up to G, and over. And we know something about that. So let me draw that pink triangle. So this is F, this is G. We know the perpendicular distance between F and G is 1 meter, so this is 1 meter on this side. We know it's 2 meters horizontally, and we want to find this, let's just call it alpha. So again, we can do that. Tangent of alpha equals, it's opposite over adjacent, so 1 meter over 2 meters. So that'll give us a phi equal to 26.565 degrees. So that helps us. So now we can actually sum the forces in the x and the y direction and figure out what some of these forces are. So I'm going to maybe just copy this again. Pause for a second. All right, so now we can start doing our equations now. So basically we have three equations that we can do with these. So we have the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and sum of the moments about a point, and we can pick which point equals 0. So let's see, if we sum the forces in the x, we're going to have 3 unknowns. If we sum the forces in the y, we're going to have 2 unknowns. So it looks like summing the moments might actually be the best bet. Let's see, at point D, there are 2 unknowns, that DG and DC. So I'm actually going to sum the moments about that point D, just to minimize the unknowns. Some of the moments about D are going to equal 0. So we have FG, so we want that, you know, with moments, you want the perpendicular, either the perpendicular component of the force times that distance, or that perpendicular distance. So I'm going to do the perpendicular component of the force since we know that alpha. So, and we're going to do out of the page as being positive. So FG will give us a positive positive moment, 'cause it's going to be out of the board. It's so we want that component, let's see, that this component here of that FG. So FGX is basically what we want, times that perpendicular distance, so times 2 meters. And then we have over at E, which will also be in the positive direction, plus that EY, which is that 26.25 kilonewtons times 2 meters. And that equals 0. So that's good. So we have one unknown. The FGX we can say is FG cosine, so SOHCAHTOA. Cosine is the adjacent one, so cosine of that alpha, 26.565 degrees, plus that 26.25 kilonewtons times 2 meters equals 0. So now I can find FG. So I'm going to pause while I do the calculations. Alright, so I just did that calculation. I got FG is equal to negative 58.697 kilonewtons. So that negative tells me that that's in compression. So FG equals 58.7 kilonewtons in compression. So now we have one of our forces, so FG. So now we can sum the forces in the, let's see, if we sum the forces in the y direction, we'll just have one unknown since that DC is all in the horizontal. So I'm actually going to shrink that down so I have more space. So we're going to sum the forces in the y direction equals to 0. So the sum of forces in the y direction, we're doing up is positive. So that y component of that FG force, so that would be, that's that 58.697 kilonewtons times sine of that 26.565 degrees. So that's that y component of that force. Plus that dg, and we want the y component of dg, so that'd be dg times sine of that phi, so 56.31 degrees, and then minus that 15 kilonewtons, and then plus 26.25 kilonewtons. And 1, 2, 3, 4, that's 4. All right, so we got 0, so now that equals 0, and we have one unknown. So now I'm going to calculate. I'm going to pause and calculate and come back. Actually, as I just started calculating, I realized that because we got in that negative number, we'll put a negative here. So now I got a dg equal to 18.03 kilonewtons. Oh, I can't write. And since that's positive, then that means it is in tension. All right, now I'm going to shrink that down. So now we have one more equation and one more unknown, so that we should be all set. So now we have our last one, which you could guess is the sum of the forces in the x direction equals 0. And let's do right as positive. So with this, we have that that x component of the FG. So that's negative 58.697 kilonewtons. And that would be cosine of that 26.565 degrees. And then we want that x component of the dg. So minus, that's 18.03 kilonewtons. And that would be cosine of that phi, 56.31 degrees. That's going to be minus DC. That's all in the X component. And then the other two ones are just in the Y direction, so we just have 3 that equals 0. So I'm just going to do the calculation and pause it, and I'll come back. So I got DC equals negative 62.5 kilonewtons. So that tells me that it actually isn't in tension, it's actually in compression. So 62.5 kilonewtons, and that's in compression. So now we found the forces are FG, DG, and DC. So now that I've done that, I'm going to go and check in the back and see how I'm doing. See if I actually got it right. Fingers crossed I didn't make any silly mistakes. So F16, 12. Let's see. Oh, F6, 12, not 16, 12. Let's see, those numbers seem way wrong. Oh, I'm looking in the wrong section of the book. F6, 12. So FD 611. Just not doing good with the back of the book. So FCD is 25 kilonewtons. Let's see, FGF. Oh, I do have it wrong. And DG, so I've done something wrong. So I'm going to go check. So I just started going through my calculations to see what I did wrong. And luckily it was at the beginning, so I found it pretty quickly. So basically where I messed up was here, is that FGX times 2 meters. I lost that 2 meters when I went down to the next step. But this is where it's nice whenever you just write everything out. So now I can go back through and fix that. So I'm going to pause while I do that calculation, or redo that calculation. Alright, so I just redid that calculation. As you can imagine, not having that 2 meter in there actually did make a difference. I'm hoping some of you caught it while I was doing it. But so FG ends up equaling negative 29.35 kilonewtons. So that would be 29.4 kilonewtons. And that negative tells us that it's not in tension, it's actually in compression. So now this mistake is going to follow through, I would imagine, for almost everything. So when we did some of the forces in the Y direction, we did FG times sine of that theta. So this needs to be changed. And let's go ahead and do that. So we get 29.4 times that. Now I'm going to pause it and figure out how that impacts the answer there. Alright, so I just calculated that through. So now my revised answer for DG is it equals 2.25 kilonewtons. And it was positive, so that tells us DG equals 2.25 kilonewtons, and it's in tension, because we just assumed they were in tension in the beginning. And now let's see where our mistake followed through here. So we did some of the forces in the X direction. So that would be this component here was wrong. So I'm going to erase that. And that's going to be that negative 29.4 kilonewtons. And I'm going to pause it and do the calculations. I was just doing this one and forgot to carry through. There was another mistake in it because we just figured out DG. So DG was right here. Let's see if I can write it in here. So that's minus 2.25 kilonewtons times cosine of 56.31 minus DC equals 0. So I'm going to pause again. Alright, so the FG is actually negative, and then the component is actually negative, so that turns that into positive. So we calculate that through, and we end up getting a DC equal to 25.0 kilonewtons. So it's in the positive direction, so that tells us DC equals 25.0 kilonewtons, and it's in tension. And so now we'll go check on the back again to see if we did our calculations right this time. So 25 kilonewtons in tension for DC. GF was 29.4, or they had 3, but it's probably just a rounding thing, in compression. And then DG is 2.25, and that's in tension. So it looks like we got it all right. So the reason I didn't go back and just redo the problem, I wanted to show you how to troubleshoot. So the way to use those solutions in the back is go through the problem, solve the problem, and then go and look at the solutions. And if you got it wrong, then just go through your steps. So like whenever I went to go through my steps, they had done the moment about G, which is fine. But then I couldn't just follow their steps. So I had to go, okay, let's see, we did the moment about D equals 0. What's going on? And I checked that first line, it looked good. The second line, I quickly saw that 2 meters was missing. And then just make sure whenever you go to calculate it for the next steps that, because then that impacted DG, which then impacted this equation. And then I had another error where I had the sign wrong for that FG. So FG, the component was at negative 29.4, but then on the drawing it was actually to the left because we're keeping it consistent, so it's actually in the positive direction because that FG is actually pointed down this way. So however you want to think about that. But so these problems, so just make sure as you study them, just try to resist looking at the back and the solutions and see if you can figure it out. So that's it.